want to come up and get snacks or whatever, coffee? All right. And also the sign-up sheet here. And all right, welcome to the Friday afternoon physics colloquium. It's my great pleasure to introduce our speaker, a friend and colleague, actually for like 15, 20 years now almost. So Eduardo loves coming to the Fridays now. So Professor Eduardo Guendelman. So Eduardo Guendelman currently works at the Department of Physics at Ben Gurion University in the Negev. Eduardo does research in cosmology, theoretical physics, and elementary particle physics. He basically has several different projects ongoing. Canada, Cosmology and Astrophysics Network for Theoretical Advances in Training Actions, Cost Action, which is actually some grant the Europeans give out. And this is a project I really support. So another project in collaboration with Tom Curtright of the University of Miami is the Bahamas Advanced Studies Institute and Conference Center, or BASIC. And every year they basically hold a conference for 2 weeks in the Bahamas, or for a week in the Bahamas, in Stella Maris, Long Island. And so I'm hoping to give a talk here this year. So anyway, if you're interested, you can talk to Eduardo afterwards to see, about getting an invitation there. So Eduardo got his BS at the University of Chile in Santiago. Then he got his PhD at MIT under Alan Guth. So if you don't know, Alan Guth is famous for introducing the idea of inflation. The idea that basically in the early universe, the universe underwent a rapid expansion. So Eduardo has worked at Los Alamos, Weizmann Institute, Ben Gurion University, and the Frankfurt Institute of Advanced Studies. And he's twice won he won second prize in the Gravity Research Foundation Essay Contest in 1989, and most recently in 2000. So, and today Eduardo is going to tell us about avoiding the swampland, explaining dark matter, and why we live in 4 dimensions. Because we do live in 4 dimensions: 3 of space and 1 of time. Okay. Yeah. Welcome, Dr. Guendelman.
I'm very pleased to be again in Fresno with my friends, collaborators. So I'm going to tell you about strings with dynamical tension and how is it related to how these strings relieve us from all kinds of constraints that the ordinary strings theory imposes on us. These are called the Swampland constraint. There is an explanation of dark matter, and there is an explanation of why do we live in 4 dimensions. That's a nice picture from some social media that commented on the last article. Okay. To start with, one of the people that started the string theory now is complaining that it doesn't work very well. It's Leonard Susskind. You have the link there. By the way, all this material is I uploaded to my research gate, so you can get it all there, right? His criticism concerns the non-existence of the zeta space in the standard string theory. And this is related to the Swampland constraint. So I'm going to discuss why the dynamical string tensions could provide a way out. This is the famous Leonard Susskind. He was one of the creators of the string theory. We live in the wrong kind of world to be described by string theory, at least from a cosmological point of view. No physicist has ever won a prize for string theory, a big prize for string theory. I can tell you with absolute certainty that this is not the real world that we live on. So we need to start over again in a, this is revelation from, right? So Susskind, he himself is working on to extend string theory to allow for at least for the zeta space. The zeta space is what describes best the accelerated expansion of the universe now, as opposed to anti-de Sitter space, right? That's the string theory seems to prefer. Okay. The Swampland constraints in the string theory are not good. We said that the first constraint is that you cannot go into the inflation, for example, that describes the early universe, cannot go very far. The delta phi of the inflaton divided by the Planck mass has to be of less than max, something of order 1. And the slope, the second one, refers to the slope of the potential, has to be rather big, right? This is the second one. And this destroys mostly the idea of slow roll that is championed by the inflation. So avoiding the Swampland and explaining the dark matter and 4 dimension, how with the dynamical tension through modified measures. And these modified measures are the things that produce the dynamical tension. This suggests that there is a reasonable, simple way to reconcile theory and experiment. What are the modified measures? First of all, we are going to discuss a generally covariant theory, but first of all, a reminder to you of a little bit the elementary calculus, right? So if you go from you go from a UV space to another XY space, right? You have this rectangle becomes the second thing here, right? Rectangle here becomes this stuff, and then you want to calculate the area of this in the second plane. Right? This is the x. You know how the area you can calculate. If you have two vectors, right? If you do the cross products, right? The area of this parallelogram is the cross product, right? And this cross product, we don't focus on this this cross product and the direction. We take the absolute value and see what is this area, right? So to get this, so this is the definition of the cross product. So you are all familiar with that, right? Something like this. Now you have the vector position, right? R of u and v is a g of uv in direction I plus h uv, and then take the derivative with respect to u, take the derivative with respect to v, and then what you do? You calculate this vector, and then you calculate this vector, and then you do cross product, right? Something like this. So the first vector is this, right? This stuff here, and the second vector is this, right? And then you do the cross product. As we say, the cross product is perpendicular. Is perpendicular to both of these and has one is the area, right? So you do, yeah. So you calculate this cross product, right? And then it comes to this, in this direction, right? So the area is, in the UV space, is this thing here, which you call the Jacobian, delta U, delta V. Right? The cross product is, in tensor notation, is the component, I of the cross product is I, J, K, J, A, where you sum over the indices that are repeated up and down. In high dimension, you put this epsilon with more indices. This object is totally antisymmetric, right? If two indices are equal, this is 0, all kind of that stuff. Yeah. So let's see, this is the formula that we have. We have this dx, dy, and then we change variables, and we have the Jacobian times du dt. From this we jump to gravity, strings, whether there should be invariant and the general Fourier transformation. So now we go to this, we found now something that transforms, but to define a volume element, we have to find something that does not transform. Right? So in general relativity, for example, also for the string theory, you have to have this object, right? And I remind you a little bit about the relativity. In relativity, you work with four coordinates, right? Four coordinates here. Ct, x, y, and z, right? In Cartesian coordinates. These are four coordinates. Dx mu is now the, right? And in general relativity, you have generalization of Pythagoras theorem, right? The distance between 2 points is defined according to the metric, G mu nu. Right? And for example, for flat space time, ds squared is minus c squared dt squared plus x squared plus y squared. Right? And this you write as a n mu nu, dx mu, where n, this tensor n is c squared minus 1, 1, 1. You can do Fourier transformation as we did. For example, you can go and put this space-time in spherical coordinates, right? You have this. Okay. So this you can do just to show some Fourier transformation. You have a Schwarzschild solution, right? And then you can do this Fourier transformation, right? Fourier transformation. The metric transform as what's called a tensor, right? This way. Right? According to this metric. And then you find that the volume element that is invariant is this. Remember that we did this antisymmetric combination of these coordinates, right? And then we have to, as this thing here we call d for x, right? And then we have to multiply it by the modulus of determinant of G mu nu. The determinant of G mu nu is negative, so the modulus is minus the determinant. So we have to see that this is a volume element, right? That is acceptable, right? So this invariant. So before we do this, general relativity has defined this connection, right? It is gamma lambda mu nu. From the connection, you define curvature. Empty space, for example, has zero curvature. The Einstein equations involve R mu nu minus half R G mu nu equals energy momentum tensor. The R mu nu is the contraction of the curvature with 4 indices, and R is the contraction with the metric of R mu nu. Okay. The volume element, we said that this was defined in terms of the determinant of G mu nu. Let's see how the determinant of G mu nu transforms. Go to another frame, right? This transforms in this way. So you have here a product of matrices. The determinant of product of matrices is the product of the determinant of each of the matrices. So the determinant transforms like this square and G. If we take square root of this, we get this, the determinant of this. Okay. And if we multiply by d for x, we saw that how the dx dy transform. If we go now to 4 dimensions, it's the same, right? It's according to the Jacobian transformation. So we see that if d tau is multiplied by square root of minus g in the prime frame is the same, right? Okay, this we can generalize maybe this I go to, maybe this is a little bit too abstract, I get rid of this part. Yeah, this is another realization of a measure density. That if I multiply this guy by dx, right, in d dimensions, it will leave me invariant. This is very simple to see because this phi here is the Jacobian of the transformation from the phi space to x space. So, why is this so interesting? Because if I multiply the Jacobian of the Colloquium transformation of the phi between phi space and x space, I get integration over the scalar field space. But the scalar fields are fields that do not transform. So this is, of course, invariant, right? And then I do some theory in d-dimensional space, for example, that has an invariant Lagrangian multiplied by the d for x, right? And then we do our beloved string theory. Right? String theory is an object that lives in a high-dimensional embedding space. Right? The string theory claims that everything is made out of strings, little strings that vibrate, split, and merge. The strings themselves are not made of anything else. They are fundamental objects with the nature is built. Now, the string tension. The string tension is a fundamental constant in the string theory. Now, it will not be fundamental. The string tension of a string is, loosely speaking, its rigidity. Is how much the string resists being stretched in a standard string theory, right? The string theory is one of the fundamental constant of the string theory. Indeed, in string theory, the tension of all the strings are the same. In the string theory is the wildest dream. All the constants of nature derive from the string constant. Okay? But now we are not going to say this, that the string theory is fundamental. That rather is derived, is a concept of integration. So what is the string theory? You have a 1 plus 1 dimensional space, right? That is the string, right? It has a revolution in time, and it's a string has a coordinate sigma, right? And evolves in a tau space. Right? So it's a one-dimensional time, and this we call D2 the surface, the two-dimensional surface has D2 sigma, right? The sigma here, generally sigma is the tau and the sigma, right? So it's a space-time, but it's a 1 plus 1 dimension, right? And then there is a metric here, gamma AB, right? So AB are tau sigma, right? This. And the coordinate of the string is x mu, right? X mu is the coordinate of the string in the embedding space, right? So, okay. And this is the famous action of for the strings of Polyakov action, right? Equation hundreds. Right? Now our idea is to take the square root of the metric out and replace it by this, right? This is as I said, this was a mesh, something that is multiplied by D2 sigma will be invariant. Okay. So let's see what we happen. If we do that, right? We don't get a good theory, right? Because I'll just do this in the blackboard, right? I'll take whatever D2 sigma, and then instead of square root of minus g, I take 5,
and then gamma AB, DAX, DBX. If I just do this, it's a trouble, because if I vary with respect to gamma AB, the gamma doesn't appear anywhere else, so I'll get equation 5 DAX mu DBX mu G mu nu equals 0. Big trouble, because either the measure is singular, this means that you have solution, either the measure is singular, this is big trouble, or this is the induced metric. You have a metric in space-time and you induce it, or this is 0. This is not doesn't give you anything that can be identified as a string theory. It's like a collapse. But it can be arranged, it can be done. And if you add this additional term here, this additional term fixes everything. And then if you, I'm not going to do the calculation because it will be long, but you show that the variation of G mu nu, of gamma IP, right? Here it appears the square root of minus gamma. Gives you all the equations, standard string theory, right? FAB is some kind of electromagnetic field stress of this potential A. Right? So you notice that it's yeah. So if you work everything is fine. Now I'm going to focus on one thing, the variation of equation of motion with respect to this gauge fields A mu. The equation is epsilon AD, right? Epsilon AD is this antisymmetric tensor, which is 0 or 1, right? The derivative of phi divided by square root of 0. And then you get the measure is equal to the measure divided by square root of minus gamma is t, and t is an integration constant. And you can read here, right? You can read here interesting comment. From my interview in FQXI about this work. This is how the string tension T is derived. It's a worldsheet constant. So it's a worldsheet constant. It means that each string can generate a different tension. Right? So it's not a universal. And right. Now it's that's how it's generated, right? And now it's you introduce now we can introduce now a really dynamical string tension, right? Because the string tension we identified as the ratio of phi divided by square root of minus gamma. If you put a source in the string tension, right? So you have this in the worksheet, right? Here, this guy, and then there is a source, J, right? JA, which is J0, or J tau, and J. And how do we generate this J? We imagine a scalar field, which we call the tension field, and take the derivative of the scalar field, right? And project this derivative onto the worksheet, right? This is the dx mu is sigma, right? And this becomes a derivative of the scalar field in the worksheet, right? Something like this. Then we put this this equation here into 109, and we can simply integrate. And then the tension becomes this scalar field, E times field. I put in 110 some coupling constant. Okay, you can always absorb it into the definition of phi. But okay, and then an integration constant di, and I is depends on the string that we're talking about, right? And from here we solve for the measure of the square root of minus g minus gamma d phi di. Okay, so we have a situation like that. And then I want to say that this theory has an additional symmetry that the string theory, ordinary string theory, doesn't have. It's the symmetry of target space scale invariant. Target space means the symmetry that involves the metric of the embedding space, not just the metric of the for example, the string theory has a symmetry that considers a conformal transformation of the metric gamma AB. But it is not the same thing. It's a symmetry of the embedding space. And this is because the string theory cannot have this symmetry because you have a string tension, which breaks this dimensional constant. Okay, it involves this, and then what do we do with the other fields? This gauge field transformed this way, this measure transformed this way, this tension field transformed this way, and this measure has, now is solved in terms of square root of minus gamma. Yeah. And so we have now we put some fields, right, and in the action, right, we put back into the action, right, this equation, right, and demand that the field is demand that there is a quantum conformal invariance of the action of the theory. Why that? Because the string theory has this property that you demand that the conformal invariance in the worksheet is verified, and this is a condition implies that the metric of the string theory or the metric of the string theory satisfies the Einstein equation, the vacuum Einstein equation. So what is the action? Now we have the serial strings, right? Serial strings with the action Si, right? And these are all kinds of external fields that you can put. So far we consider this, right? Here I replace the square root of minus g, the phi measure by the solution that we found before. And then these other fields we consider trivial, right? Because we have already too much to handle, right? So we have now a string, embedding space which is the product of this for the string I times this, right? So we define a measure that is like that, a string metric that is like that, string embedding metric that we have, right? So suppose that we have now two kinds of strings with the T1 different than T2. The two metrics have to satisfy both the Einstein equations, right? The two of them at the same time. They are related by a conformal transformation, but the Einstein equations are not invariant under a conformal transformation. So this is a non-trivial condition on the field phi. You see here, for example, the two metrics are related by a conformal transformation, right? And then this relation between the two conformal transformation reflects in equation 117. From here you can solve the field phi, right? And from the solution 118 you can reconstruct the tensions of the two fields, of the two strings, right? So you have the equation 119 and 120.
right? And we take the two tensions to be positive, T2 minus T1 is positive, omega square we take it as positive, right? And we have to take, for example, two spacetimes that are conformally related. This do the first exercise like a metric of Minkowski space, which with eta 0, 0 equals 1, eta 0, I is 0, eta ij is minus delta, right? And then the second metric, we take the metric of Minkowski space as after a special conformal transformation. Special conformal transformation is something similar to stereographic transformation, okay, but a little bit more complicated because it's space-time. And it's written in equation 123. The relation between the two conformal metrics is given in this equation 124, and the conformal factor is this factor here, omega square, right? That is written in below 123. We replace this equation in the equation for the two tensions, right? The first tension is given by equation 125, and the other tension is given by equation 126. I can take the A mu is a D vector, right? So I can take I do first exercise, which is a little bit more complicated than the second one that I'm going to do, where A mu is just a time-like, right? So A mu is a constant 0, 0, 0. We just have the time. And then if I take the limit, A goes to 0 and T2 minus T1 goes to 0, such that the ratio K is a constant, I get in this limit that the two tensions are equal. And the metric, the embedding space metric, is defined by equation 128. It doesn't satisfy the vacuum Einstein equation, right, because it is non-trivial now. Okay, if we go away from this limit and T2 minus T1 is small but finite, at large times these two surfaces of the string theory, they start to diverge. And if you see, there are 2 points where the string tensions go to infinity, right? Where the denominators of you see that the denominators of 125 and 126 have go to 0 at different points and two hypersurfaces. And at those points, the string tension goes to infinity. Okay, and these are the surfaces, 130 and 131. And I'll write them as a equation 133 and 135. These are two hyperbolas, right? Something like this. And one is inside the other, right? And they merge. At the large time, they merge. They become very close to each other, right? So the radius is this square root there, right? The radius of the hyperbola, and the other radius is like this. The distance between these two radiuses goes to 0 as t goes to infinity, right? And this equation, for example, everything is merged. It goes into, say, the surface 135. If you look at the 135, is something very interesting, because you are resolving one of the problems of the string theory. This is this is generating a de Sitter space, This is the zeta space that the famous string theory put in G. Now this is this surface. If you look at the metric induced in this surface, this is the zeta space. This, as Lenin Haskin said, ordinary string theory doesn't give you the zeta. Here you got it. Okay. And this the zeta space has a classical you can do a Euclidean region, imaginary time region, where the hyperbolic motion is circular, right? Circular motion here. This is what they call the tunneling region. And then the universe is created as a de Sitter space from the points A and B, right? It's classical order. Okay. And now there is a simpler example that I wanted to show you. I take vector A mu timeline, right? So the A mu, this object here. A square is equal to A mu, or if you want A mu, is equal to 0, right? And this is achieved for A mu equal A 0, 0. Okay? I do the calculation and then everything is much simpler. Everything is much simpler. You see that the tension of one of the strings is given by this. Tension of one of the strings is this. And the tension of the other string is given by this. And the region, the points where the string tension becomes infinity is x minus t equals 0, right? For both cases. X minus t equals 0, and the other one is the other denominator goes to 0. So there are two parallel surfaces moving with the speed of light, right? And between these two surfaces, the tension is finite, and then it goes to infinity. You in this simple model, you can avoid the infinity. How do you avoid infinity? Because you say that before this, you define this time-like variable x minus t, right? X minus t, and then when there's an a negative, and then a little bit before this goes to infinity, you stop it, and then you create a periodic boundary condition, right? So, and then you shift by a value delta 1, like this. So you avoid but you can make the tension as big as you want. And then you have this situation that the tension can become very big. Now the Planck scale is related to the string tension through this relation, right? Kappa square is 8 pi g equals 1 over the Planck scale. So if the string tension is going to infinity, the Planck scale is also going to infinity, right? So this is what Thea wrote, because he interviewed me, the FQXI report she wrote in social media. That this I will avoid because it's really too much. So now the point is, can the dynamical string theory recover the Swampland? I mean, avoid the Swampland, right? So you recover what the string theory is put into the Swampland, and you want it because it's good for physics, right? Yeah. The first constraint is this: that you cannot go too far in your inflation, because how far can you go in your inflation is delta of phi divided Planck mass less than something of order 1. with the M being the plant mass. But the plant mass, we say, in the region where the string tension goes to very big, the plant scale also goes to big. So this constraint is not constraint, because we made a possibility of regions of space, time, yeah. Also, due to the difficulties of consistently constructing the metastable de Sitter vacuum, they proposed another constraint, that the plant mass times the gradient of the scalar field is bigger than something, right, related to the potential. So it's the logarithmic derivative of the potential. But now, again, this is not constrained now because the Planck mass, because we show that the tension goes to infinity and the Planck mass also goes to infinity. So you get rid of this constraint as well. Okay? Okay. So this is the conclusion that the constraints become irrelevant or very weak. So dynamical tension string theory is friendly to inflation and dark energy. Okay. Because in this dynamical string tension, you have the possibility of Planck scale to go to infinity. At this point in space-time, where the Planck scale goes to infinity, the Swampland constraint disappears. Tensions to infinity. Tension going to infinity represents the target space scale invariant. So it's well motivated that you have this situation, right? Now you have a similarly breaking because you have a scale invariance, you have a spontaneous breaking scale, but then you recover because tension transforms. But if it's infinity, it transforms from infinity to infinity. Now, another idea concerning dark matter. I was in Princeton talking to Professor Maldacena on strings with different tension. And he observed that the ordinary string interaction decoupled for strings with different tension, which led me to the idea that the strings that constitute the visible matter are the visible, have a certain string tension, and the other strings with different tension, we cannot interact with them with ordinary strings there, with the ordinary string there. Why? Because the ordinary string interaction cannot change the string tension. The string tension just split, or all these ordinary string interaction cannot change. So if the strings have different tension, they cannot interact. So they must be, if they exist, they must be dark matter. Furthermore, if both visible matter and darker strings share the same space-time compactification, they share the same space, right? And they must share also the same compactification because the strings are formulated in a 6-dimensional and a high dimension. So you have to compactify, but they have to share the same compactification. Now, in string theory, the compactification organizes the particle spectrum. So if that's the case, the dark matter should consist of dark copies of the standard model, because the standard model is what arises from compactification, a very particular compactification. So there was some comment on this. And I have just time for the last subject. This is the social media commenting on this, right? Yeah. This is some similarity what happened in the standard model, that you have several families, and then the people start, oh, but why don't they communicate? If they communicate, there's a big trouble. And then Sheldon Grasham, Dilopoulos, Mayanis figure out that there is a way to suppress the interaction between families in the standard. But they still interact. And now we have the other families of this standard model
They are not families within the standard model. There are other families, other copies of the standard model do not interact. The only possibility would be through this new field, the tension field. But, okay, something very weak, which makes it into dark matter. Okay. So these are the reference for that paper on the dark matter as strings of different tension. Okay. Now the last subject is how do you get the 4 dimensions? Because, okay, the idea is to formulate the effective theory with strings. I show you that you can formulate a theory. Everything was motivated by going to the modified measure, right? Something like this. And then we consider effective action of this way. And we consider the closed string, in the strings are closed strings and open strings. The closed strings are supposed to give you the gravity. So they are considered into the first term. And the second term relates to the open strings, something like this. And the equation for so now we want to somehow say that the scale invariance, the target space scale invariance holds, right? And the matter, the string is described by what's called the Nambu-Koto action, something like this. Right. Something like that, right? And then we want this additional piece considering the open strings, right, here, to be invariant under this action. The ordinary string doesn't, it has this equation, right, this L of strings is given by this way. Now we put, instead of this, we put the 5 measure, right? And we demand that this symmetry holds, right? This symmetry holds. For that, the L string has to transform the same way as the curvature, right? The curvature transforms in this way, right? And this L string transforms in this way if you calculate the transformation of the metric, of everything, right? So the metric. For this to be the correct transformation law, so it has to be transformed the same as the curvature. This determines that this number here has to be 1. This is only possible if d equals 4. So this is an argument to show that this kind of theory leads us to, I wouldn't say it's a proof, but it's an indication that the theory, effective theory, has to be formulated in 4 dimensions. There's always a puzzle, why the string theory that is formulated in the 6th dimension or 10th dimension has to go to 4 dimensions. Well, this is an argument from the invariance. Okay, so let's see. Yeah, so these are all kinds of references. Yeah, this was an essay to Graduate Research Foundation. It's now published in International Journal of Physics D, that got the honorable mention. And then there is a longer version in European Journal of Physics. The other issue that we're working now with the DAC is if you know that the string tension produces non-commutativity. Now if the string tension is local, is changed, is local. So the non-commutative contributes to the 0-point energy. The effects of this in the non-commutative, the dynamics of the string tension
will translate into dynamic of the zero-point energy. And we hope with Douglas we will do something. Thank you very much for your attention.
All right, so we have time for questions. Was it the cloud from outside? All right, so, Eduardo, so the individual strings, the open strings, each individual string has the same tension throughout, it's just different strings have different tensions, is that the point?
Yeah. This, well, in the last part of, I ignored this because I want the tensions, the theory to have a strict invariance and the scale invariance. So I ignored this effect of this different strings just for the last part, right? Just to have an argument. Now, if you have many copies, it's almost like many copies of the strings that could constitute the dark matter. This would be almost like a scale invariant, right? Because you transform from one to the other. Anyway, the last part is like a suggestion, right? There is no proof.
Other questions? Comments? Okay, now let's thank our speaker again.